So for my final project, I wanted to learn more about something I've always been curious about for a long time. This is something that's been used in the software engineering field for decades and is becoming more and more commonly used across various different industries. That's simulation, but specifically in the field of physics engines. Physics engines provide a way to replicate real-world objects and concepts and manipulate them and test them in safe environments. Physics engines are used to create everything from video games to NASA shuttles to construction projects. It's far easier to find a problem and fix it during a simulation than it is once you make a million of a product and find an issue with it. Um, just about every single moving part these days goes through some sort of simulation. Every car part, every helicopter blade, every new building that gets put on campus, even a lot of software has to go through simulations before it can get put on the market. Boeing's having issues with this right now. But instead of listing all the ways and places simulations are used, I wanted to learn more specifically about how they work internally rather than just where are they used. These engines can be broken down into three main processes: the world, the objects, and the connections. The world piece is the first piece. It's the overall world or universe that your simulation is run in. This defines how objects interact with each other. The world is the laws of physics, what your simulation is simulating, how it's simulating it. This includes everything from objects in motion to the forces on them to when objects collide, how the heat transfers between them, when there's friction, when there's not friction, electricity, chemical interactions. I could go on and on and on, but it all depends on what sort of simulation you're doing and what you're trying to simulate. But with simulations and physics engines these days, we can replicate all these processes and different behavioral patterns that we see in the real world. The next piece is objects. Objects are just that. They are different things. They are points in space that are defined as an object. They have different properties. You can program whatever their mass is, whatever their density is, different friction coefficients, temperatures, heat flow rates, um, anything like that. You give them different sizes, different shapes, and they can be any singular thing. This can be a cup, it can be a computer, it can be a keyboard, as long as it is one object and not multiple objects, which is where we get into our next point, which is connections. Connections are what really makes a physics engine a physics engine. Connections are how to make just about any object, and it's how they're bonded. Um, these what we'll call strings, keep objects together. It, Connections can be various strengths and various elasticities. How strongly are these two things connected? A string, for an example, could be a little piece of twine, things causing two objects to break easily apart. Or it could be, a strong rope property that, takes a lot of force in order to pull apart. It also defines, do they pull back together? Do they remain apart once they get pulled apart? If they get pulled back together, how fast they get pulled back together. A common example is the cloth example. If I wanted to make a simulation of dropping a cloth, what would that look like? I wouldn't just create one object that's a flat sheet of mass. I would create a whole bunch of little small objects, a whole bunch of little points in space, and then connect them all individually with various connections, each one connecting to its neighboring object. And this allows something like a cloth to be replicated and simulated. Because if I didn't make the connections and I just made one big sheet of mass, that would essentially mean a piece of cloth is the same as a piece of steel. So that's a big way that physics engines use connections in order to replicate what we see in real life. So what programming language are these written in? Well, I found that any object-oriented programming languages will pretty much do what you need to do in order to recreate your world and your objects, as well as create the connection strings. So anything from your C's, your C++, C, C Sharp, to Java or JavaScript, any of these will really get the job done. So just how big is the field of physics simulations? Well, there's about 77 different open source physics engines that are available for anyone to download and play around with, and use on their own machines if they have the processing power. As terms of businesses and proprietary simulations, well, there's possibly hundreds, likely even into the thousands range. The businesses quite often these days are developing their own physics engines to fit their own simulations and suit their own needs. Every different car company has their own. BMW would use a different one than Ferrari, than Tesla. Even NASA alone develops all kinds of their own different types of simulation software. But each different part that gets developed by a company has to go through different types of simulation. They have to go under different types of, for example, in NASA, they have different stress testing, to test the stress of when you go off into space, and they have different testing for how is this going to interact with the chemicals around it. What's the heat transfer rate? Is this going to be structurally solid? So all in all, every shuttle that gets sent into space goes under currently 997 different types of simulations and different types of physics engines. So while it might be flashy and exciting to talk about all the new and powerful engines that are being used in video games these days, the practical application of these just reaches so much farther, impacting everyone's daily lives. Whether we're using them to learn more about natural phenomenon or watching a car crash in slow motion, the three main parts, the world, the objects, and the connections of physics engines, allow us to really replicate anything that we can see in the real world and give us all kinds of different data that we would not otherwise be able to access.